Thanks everyone for coming to my talk. Today I'm going to do a progress update on Project Hydrogen. A quick introduction about myself. I'm currently a tech lead on the machine learning core team at Databricks. And I was also just working on data science and data engineering just at Databricks for about 2 years. I'm a committer and PMC member of Apache Spark project. I'm mainly working on the advanced analytics part, like MLlib, Spark R, and PySpark. So first, I want to explain what is Project Hydrogen. It's last April, I moved back from the data team to machine learning team. And we had a brainstorming with Reynolds and Matei at Databricks about what are the missing pieces and to make Spark and AI work together, right? And then we came out with several ideas. We socialized it with the community on the user and dev mailing thread. And this came the Project Hydrogen, announced last year at the Spark Summit. The goal is really say, we want to unify state-of-art AI and big data workloads. So it has 3 main components. The first one we call it barrier execution, and second, optimized data exchange. Third, accelerator-aware scheduling. So I will explain each of the components later. So then the question is, why Spark and AI? It's kind of a funny question because you are in a conference called Spark plus AI Summit. But still, why? We know Spark is the default engine for big data processing. Many companies are using Spark to process maybe terabytes, petabytes of data, right? And AI is actually in everyone's daily life. So you take a photo and it's optimized by AI. You browse websites, you take a personalized results, right? So AI is everywhere, but is AI good enough? This is given the audience here. Actually, I want to do quick experiments. Hey, Siri. I heard one. How about, OK, Google? I think Google is silent. Just a response. But anyway, you see, there are false positives, right? So AI need to be better. And how to make AI better? A quick answer is better AI needs more data, right? So with deep learning, deep neural networks, it can scale super well with the amount of data you have. Just feed the same network with more data, and you may get better results. And this is why, well, when people are working on AI, they need to go distributed. They need to work on a large amount of training data sets. And when they go distributed, they are facing issues with handling big data. This is where Spark really shine. And this is where Spark and AI cross each other. And then, well, we know, well, big data and AI, but why we need a Project Hydrogen? It's just because simple things still doesn't work as expected. I want to show 2 stories. Suppose I'm a data scientist. I should be able to build a pipeline that fetch training data from production warehouse, and then run distributed deep learning training and to get a model, right? Simple training scenario. Second, after I have a deep learning model trained, I should be able to apply it to a distributed stream of events and enrich the events with my predictions, and then serve downstream applications. However, if you think about how we can do it, it's not trivial. For example, for training, first, you need to load the data from production warehouse, Delta Lakes, S3, Kafka, Azure. This is where you use Spark. And then for model fitting, you need a distributed GPU cluster for distributed deep learning training, and you need a different framework, something like a Horovod Distributed TensorFlow, right? So how you connect them together? That's not a trivial question. And how about just using 2 separate data and AI clusters? I use a Spark cluster to fetch data. I use a deep learning cluster to do training. But as a user, I need to maintain some glue code. I need to, if there is an issue, I need to debug here and then debug there. So that really just, say, breaks my workflow. This is not something I want. And also, if we keep two clusters, one for data, one for AI, what happens to the second story? Streaming model inference. So I want to read data from a Kafka stream. I want to apply my model and send the data back to a Kafka. If I use separate clusters, how can I stream the data from the Spark cluster to the deep learning cluster? And how I return the results from the deep learning cluster back to Kafka? So those are non-trivial. An ideal solution is we have a hybrid Spark and AI cluster. If I can do both big data and AI in the same place, that would be ideal. But however, it just doesn't work out of the box. So I put a link here. I'm not going to show a demo. It just say, I showed previously why things could break. And this is where we need Project Hydrogen to fill in the major gaps between Spark and AI. And those are the three major ideas we proposed. And today, I'm going to present updates from this project. And I want to just present updates from two angles, wearing two hats. One is as a Spark contributor, I want to present what features we delivered under Project Hydrogen and what features we are working on, how do they look like. Right? So second, as a data engineer, I'm a user of Project Hydrogen, how I built features on top of Project Hydrogen. What are the lessons I learned and the best practices? And let's still go back to the story. The first story is distributed training. This is what we want to achieve. Use the same cluster, load data using Spark, still feed the model using a distributed deep learning framework, and save the model out. It's a simple flow. And the first feature we need is called barrier execution mode. And this is because traditionally Spark and those distributed deep learning frameworks, they have different execution modes. Spark use MapReduce. And under MapReduce, each task is independent of others. And it can be scheduled independently, it can fail and recover independently. But for distributed training, it's different. So usually, the worker starts together, and they talk to each other frequently during training. And if anyone failed, and it's pretty hard to recover them. So, and they are optimized for very frequent communication to exchange the gradients and to faster model convergence. Barrier execution mode actually is a major change to the Spark job scheduling. And we also call it GONE scheduling. So essentially, it can start all the Spark tasks all together. And we provide sufficient info and tooling so user can hybrid in a distributed deep learning job as a Spark job. And it will monitor the job and cancels and restart all tasks in case of failures. This is barrier execution mode. I will go briefly over the APIs. The first one is just rdd.barrier. It will trigger a barrier stage and basically say, within this stage, all the tasks should be scheduled together. If you don't have enough tasks, just wait. And within the task closure, you can get a barrier task context, which you can use to get more information. And we also provide tooling like this one, context.barrier. Essentially, context barrier tells all tasks to wait until all the tasks reach this stage. For example, if you want to do some data preparation, and you want to make sure before you trigger all the tasks, the data is there and prepared by all the workers, you just call context.barrier and then move on to the distributed training phase. The next one is called, from the context, you can get all task infos that include the IP addresses of all the workers. In this way, you can actually schedule a distributed deep learning job as a hybrid Spark job. And for example, for this one, I can say, if I'm the first executor a task, I will just trigger this MPI job. And all the other tasks, they just wait at the context.barrier until the training job finished. So those are the simple APIs, but those are super helpful to build integration with deep learning frameworks. So how we integrate? This is outside Spark. Basically, we pick a deep learning framework, and we picked Horovod. Horovod is a Linux Foundation AI-hosted project, and originally developed at Uber, and it supports TensorFlow, Keras, PyTorch. And it only requires very little modification to single node code. So if you have single node training code, you only need to add a few Horovod hooks and to make it distributable. And then it has a very high performance I/O through MPI and NCCL. And the best thing about Horovod is it uses all reduced pattern that actually it has the same convergence theory as a single node. So you don't need to worry about when you spawn a cluster of 100 nodes, you can only get something like 10x because the convergence is slower than single node. But there are some limitations. First, user need to use MPI run to launch a job because Horovod uses MPI, and user need to provide a training script. This is example command line. As a user, you need to run if you use Horovod directly. Definitely, this is not what data scientists want. Also, working with a script, it's hard to do some frequent updates. It's not in something like a convenient as an interactive workspace, like notebooks, right? So we look at Horovod, and we think about how we can integrate Horovod with Project Hydrogen. We released a feature called HorovodRunner in Databricks Runtime 5.0 for machine learning. It's basically, we run Horovod job as a hybrid job using hybrid Spark job using barrel execution mode. And with this API, we can actually hide the cluster setup, scripts, MPI command line from our users. Essentially, they only need to provide a train function, for example, like Horovod train HVD here. And then they just call Horovod, specify the number of workers you want to use for distributed training, and then run this job. And they can do that in a notebook, and they don't have to just write down the Python scripts. OK, so I want to briefly talk about how we implement HorovodRunner. And with barrel execution mode, actually, it's pretty straightforward. First, user provide us a train function. We use Cloud Pickle to pickle user's function, and we broadcast it to Spark workers. And we also inspect the code and warn users if, well, there are some potential issues. For example, there is a huge object. We will just give the user a warning ahead. And then we launch a Spark job in barrel execution mode using the number of workers user asked. And in the first executor, because I already have all the IP addresses from this, of the workers in this job, I can just launch a Horovod MPI job. We can generate the commands for users. User doesn't need to know it. And then we monitor the job. In case user want to cancel it, there are some task failures, we ensure there's a proper termination of the user program, like TensorFlow program running outside Spark. So, but there are some limitations. It's first, the feature was really tailored for Databricks runtime machine learning environment. We know that we pre-installed TensorFlow PyTorch. We have Horovod pre-installed, passwordless SSH logins, OpenMPI, NCCL. We also know that the cluster is running Spark 2.4, right? So we also know about our GPU cluster configuration, and that's very tailored for a specific environment. And the good thing is, in Horovod 0.16, and Horovod released a feature called Horovod.Spark. It's similar to HorovodRunner. It takes a Python function and it runs the Horovod as an embedded Spark job. And their implementation is actually more general. There's no dependency on SSH, and there's a system-independent process termination implementation, and it supports multiple Spark versions. Also check out HorovodRun. That also simplified the user interface, so they don't need to do MPI run. So basically, there are two implementations, and as a user, and which one you should use. So The good news is engineers at Uber and Databricks, we are already collaborating on improve the integration between Horovod and Spark. And essentially, we want to merge our design and code development into Horovod.Spark inside Horovod main repository. And HorovodRunner on Databricks will just use Horovod.Spark implementation plus some Databricks-specific features. Then we want to support both barrier execution mode and GPU-aware scheduling. So those are the features from Project Hydrogen. So stay tuned for an official announcement from us. Then we mentioned GPU-aware scheduling or accelerated-aware scheduling. That's another component under Project Hydrogen. Basically, those accelerators, we learned from yesterday's David Patterson's keynote, we need those accelerators for accelerating specialized workload because the CPU power just doesn't increase anymore. Right? So, and to utilize those accelerators in Spark, Spark need to be aware of what accelerators are assigned to the driver, to the executors, and how to schedule them according to user request. And why? The cluster managers, like Mesos, Yarn, and Kubernetes, they already support GPUs, but why Spark still need to be GPU aware? This is because Spark still has a scheduling layer inside Spark itself. Consider a simple case. What if I need a Spark job? One task needs one GPU. On the left node, that's executor 1, it has 2 GPUs, it has 2 tasks. And if task 0 took GPU 1, and task 1 tried to take GPU 1 as well, then it will cause a conflict. They try to share the same GPU, they may just run out of memory on both. Right? So the second node, what if Spark scheduled 3 tasks on this node, but there are only 2 GPUs? No matter how collaborative those tasks are, they cannot really figure out a working solution because there are not enough GPUs on this node. There are a couple of workarounds. For example, before we have GPU scheduling, we can limit Spark task slots per node to 1, to only 1. So then there will be at maximum 1 active tasks, and this task can safely claim all the GPU cards on the node. But this one may lead to resource waste if you cannot fully utilize all the GPUs. Or user also need to write multi-threading code to maximize the data I/O in order to load the data fast enough. And a second approach is just let running tasks themselves to collaboratively decide which GPU they should use. Maybe just put a lock on the disk and then check out which GPU is available. But essentially, this is error-prone approach. So what's the new proposed workflow under this GPU-aware scheduling? First, Spark Cluster Manager, standalone Mesos Yarn, they should be able to auto-discover resources on the worker nodes, on the nodes. And then users submit the Spark class application with those resource requests. For example, I say, I need 1 task per GPU. And Spark will recognize those requests and pass those requests to the cluster manager, and cluster manager allocate executors and with those additional resources, possibly with resource isolation. Then Spark registers those executors, and the Spark scheduler knows what are the available executors. When user submit the Spark job, and the Spark will just schedule tasks on the available executors, and in case you're running out of executors, and you may just use dynamic allocation to get more. Then within the task closure, user can retrieve which GPU is assigned to my task. I just follow this assignment, then I won't have any conflict. The cluster manager will monitor the executors and recover failed executors. That's a normal Spark feature. How to discover and request GPUs? First, admin can specify this auto-discovery script. And those are the 2 configurations. And we call Spark driver resource GPU discover script or Spark executor resource GPU discover script. And for NVIDIA GPUs, that would be just NVIDIA SMI, a bunch of commands. This is a working in progress PR. And how user can request GPUs at application level, when they run Spark submit, they can send out use those configurations to say, I need how many GPUs per executor, I need how many GPUs for my driver, and how many GPUs per task. So those are the proposed approach for user to make the requests. And then at the runtime, how user retrieve the assigned GPUs is basically you get the information from task context, and you can call context.getResources, and it will return a resource mapping. If you say, give me the first GPU, and then I will use it in my TensorFlow code, just with TF device and with the assigned GPU address or name, which is maybe TensorFlow compatible, and then you can use that GPU for training. But a major work to support GPU scheduling is actually on the cluster manager support. Each of the cluster manager need to be able to take requests from Spark submit and then allocate executors and then monitor the executor usage. For standalone, for example, for standalone, we need to implement those auto discovery, and for Yarn, we need to upgrade to Yarn 3.2, and which has GPU support. And Kubernetes, we may need to think whether we want to integrate with the pod template in Spark 3.0 to simplify the configurations. Right, so Mesos also has some previously implemented GPU support. We want to see how we can make a compatible migration. So each of the components has some challenges, and for each of the components, we also have a committer assigned and in order to sever the project. Those are the JIRAs. If you're interested, you can just go to the JIRA for details. An interesting part is actually the Jenkins support. Spark runs integration tests, unit tests with every single PR, and we want to support end-to-end integration tests for GPUs, and that requires adding GPUs to the Spark Jenkins machines. Those machines are hosted by Berkeley Rise Lab. And this is actually not trivial, because you want GPU scheduling in Spark, but if you want to have integration tests, you kind of still need GPU scheduling in Jenkins to make it work. And also, you need the GPU cards and to plug in them. Actually, we talked to Shen from Berkeley, who maintained those Jenkins machines, and he told us, OK, there is a very strong requirements because the power cannot be plugged in on the top of the GPU cards or on the side. But luckily, we have NVIDIA in this collaboration. They donated the very latest Tesla T4 cards and to Berkeley Rise Lab, and those doesn't require extra plug for the power. And this is really great. So we currently focus on GPUs, and this is mostly used by deep learning applications, but people also want to have other types of accelerators. We try to make our interfaces general enough so we can support other types of accelerators in the future. For example, the GPU name is not a hard-coded resource type. There's nothing special about this name. User can just use Spark executor resource type, arbitrary name, and tell the cluster manager how to discover the accelerator resources. And then get resources, as I mentioned, just return a resource mapping. From the key is the resource type, and the values are assigned addresses for this task. There are some nice-to-have features, but it's currently not included in the current SPIP. The first one is resource request at task level. So ideally, if I have a very complex job, I start with some data processing, joins, and the group by, and then I want to start a deep learning job. For the first half, I don't want to use GPUs. For the second half, I want to use GPUs. Currently, to limit the scope, because it's already very big, we allow resource requests only at application level. Within the application, the per task resource request will remain the same. And we treat each GPU as a non-divisible unit. You cannot really just have fine-grained scheduling and say, I want to have half GPU. So that's currently not possible. And some affinity, and I want to GPUs on the same node or GPUs on the same rack. Those features are currently not included in the SPIP, but they may get implemented in the future. So one more thing about distributed training before we move to the next story. I want to talk about the data flow. We now have, say, execution mode, and we have GPU scheduling fit into this deep learning and the big data integration, but how I pass the data around. The recommended approach, based on our experience, is currently use Spark to do some loading pre-processing. And then you can save your pre-processed training data to a shared storage, and using format like TF records or Parquet, and those are readable by those deep learning frameworks, and Parquet can be read through a library developed at Uber called Petastorm. And for shared storage, you can use S3, Azure Blob Storage, HDFS, and NFS. So because in some training mode, you want each of the worker be able to sample all the entire data sets, and that will help the convergence. And then when you load training data into those deep learning frameworks, they do not work that well with remote storage. For example, TensorFlow, it supports S3. But if you test the performance, it's just a single connection, something like 300 megabytes per second, definitely not fast enough for your GPU. And we recommend a solution is to use high-performance Fuse client to mount your remote storage as local files. And because those deep learning frameworks can work super well just with local files, right? And the deep learning applications usually just do sequential read, sequential write, or random read. And you can highly optimize your client for those operations. For example, for S3, we recommend using Goofies. And for Azure Blob Storage, we recommend using Blob Fuse. So that's make users' life much better. They don't need to think about how to use SDK to fetch data from remote. Let's move to the next story. We call streaming model inference. Essentially, what we want to do here is using a single Spark cluster, load a stream from Kafka, apply a deep learning model, and return the results back. And here this is fall under this optimized data exchange proposal. And our recommended solution is to use high-performance data exchange and to optimize this workflow. And because if you don't exchange data, actually it's not possible to integrate Spark and AI. You have to pass some data from Spark to AI, and performance really matters here. A simple answer here is just a Pandas UDF. It was introduced in Spark 2.3, and it used Arrow as the underlying format for data exchange, and user can utilize Pandas for vectorized computation. So this is a performance comparison we published after Spark 2.3 release. You can see the little bar there is Pandas UDF. The lower, the better. Actually, we saw about more than 200x performance improvement by switching from PySpark UDF to Pandas UDF. And it's also good for distributed inference because you just need to declare the prediction logic as a Pandas UDF function. Here you say a defined function called predict, taking some features and return the predictions. And then you can use Spark to read a Kafka stream and apply this model and append a new column just called predictions. And that's it. It's super simple, right? But still, when we try it, and in real use cases, there's still something that doesn't really work well. The first one is sometimes I want to return a complex data. For example, I want to return the predicted labels and the raw scores together, right? But Pandas UDF didn't support returning a StructType. But this is implemented already in master, and it will be available in Spark 3.0. And you can return a Pandas data frame with multiple columns. That helps with the model inference case. And then we look at the performance. we found out the performance is not that great. It's essentially, if you monitor GPU utilization, it's on and off. What happens is, this is a feature called data pipelining. Essentially, if you are doing both I/O and compute, if you do this one by one, let's say you load a batch, you apply deep learning, do deep GPU computation, you apply another batch, fetch another batch, and apply GPUs. And actually, the GPUs may be idle just for 50% of the time. So you definitely want to do GPU data pipelining. So while you are running GPUs, you keep fetching the data from the backlog. So this is what we call Pandas UDF prefetch. And the feature is already implemented and enabled by default on Databricks Runtime 5.2. And theoretically, for I/O and compute balanced workload, you should see about 2x. So basically, if the I/O and compute takes the same time, and you align them well, that should be the upper bound of the speed up. And we actually observed 1.5x on real workload. And this feature will be also available in Spark 3.0, and just bring this performance optimization to all the Spark users. The next overhead we observed is this per batch initialization. Remember, if you say, I want to define a predict function using Pandas UDF, you still need to first load the model into the memory and apply this model. But this function is called per batch. That means it's a constant overhead if you always need to reload the model from disk or from other external storage. And what we propose is really say, make a new interface to Pandas UDF that can take an iterator of batches. Then you only need to load the model once, and then you can go through all the batches and yield the results. And so in this way, you can improve the performance even further. Oh. The next item is we really want to standardize on the Apache Arrow format, because many accelerated computing libraries now support Apache Arrow. For example, Rapids AI from NVIDIA. It includes the CUDF library, and that can use GPUs and for accelerated computation. And currently, the community is discussing whether we should expose this Arrow format in a public interface to simplify the data exchange between Spark and other frameworks, and to reduce the data copy or data conversion overhead. You may just pass over off-heap pointer to the other application who can recognize the Arrow data there and do some computation. And in this way, we can also just say plug in some vectorization code. And that's specialized for certain environment, but may not be general enough to get into the Spark main repository. So this is a SPIP currently pending vote. And I think that's basically it. And the entire project Hydrogen, the ideas are not, I won't say the ideas are original. It's already done in many other frameworks, and it's also just previous attempts from the community to bring this big data and AI together. And there are also many Spark committers and contributors who helped to discuss the project proposal, design, and the implementation. So there is really a long list of names. And for example, Xingbo, who implemented the barrier execution mode, and now is working on the kernel part of the GPU scheduling. And Thomas helped a lot on the Yarn support for GPU scheduling, and Andy and actually just make the donation happening, and it's really a lot of contributors. I want to thank all of them. And yeah, that's it. So any questions?
Thanks, that was a great presentation. A quick question on barrier scheduling. On a very long-running job, it's all or nothing mode. Did you see any need for checkpointing or saving the state so that you can recover?
So barrier execution modes really just focus on the scheduling. Checkpointing is a user-level logic. For example, you can do distributed deep learning, and both TensorFlow, Keras, PyTorch, they already support checkpointing. And what you need to do is to checkpoint to a remote persistent storage. And next time, if the job failed, you restart, it can pick up from the previous checkpoint. Yeah, I think that's it. Thank you.